So this is an example of two different kinds of equations that we've learned in this unit. This is from the workbook, page 261, and it's example C. The workbook shows it worked out, but I'll work it out for you. This is 3y minus 4 to the 3/5 minus 4 equals 50. This is an example where the exponent is in the base, and therefore our job is to try to isolate that exponent. We're going to begin by moving over the 4, adding 4 to both sides, and then we'll be getting rid of this 2 over here. So we got 3y minus 4 to 3/5 equals 54. Now divide everything by 2. So what we're doing is isolating the part of the equation that has that fractional exponent, and that's this part right there. So that's the purpose of moving over the 4 and the 2. This leaves us with 3y minus 4 to the 3/5. 54 divided by 2 is 27. I don't know how to make an extra page on this. How do I make this bigger? Okay, the next kind of example is from the workbook. The workbook, page 265. So the example we did before, the variable was the base. This example is with the variable as the exponent. It's still an equation though. The objective is still to get x by itself. The way we do this is by rewriting both sides of the equation with the same base. So 1 over 9 can be written as 1 over 3 squared, which is really 3 to the negative 2. This is being raised to the x, making it 3 to the negative 2x, since we can just multiply those exponents. On the other side, 27 is 3 cubed to the 1 minus x. We're going to multiply these exponents, meaning distribute, so that's 3 to the 3 minus 3x. Now that the bases are the same, we can choose to focus only on the exponents and set them equal to each other. Adding 3x to both sides here, x equals 3. A very typical kind of mistake in this kind of problem is something I'm going to explain in the next slide. Sometimes when we have variables in the exponents, which, by the way, those kinds of equations are called exponential equations. Let's change that, make it a 16. Students will look at a problem like this and they'll think, oh, if I raise 4 to the second power, that's essentially getting me a common base, and I can just say this is 16 to the x plus 1, and that way it'll be 16 to the x on this side, and they will have the same base. The problem with the logic here is that you're raising one side of the equation to a power. You are changing the value of this side of the equation, but you're not changing any value over here. So your equation is now unbalanced. The correct way of doing this would be getting a common base by kind of, scaling down. 4, what is that a power of? Well, it's a power of 2. That's 2 squared to the x plus 1. 16, well, that's 2 to the 4th to the x. So you essentially have 2 to the 2x plus 2 equals 2 to the 4x, and now you can use the method we've been using of just making the exponents equal to each other because the bases were the same. But as you see, you want to go lower, if anything, than the bases you already have, not higher. Of course, there's another way this problem could have been done. You could have chosen to make the 16 just 4 squared to the x, and that would have given you 4 to the 2x equals 4 to the x plus 1. You should get the same answer then when it's done this way. But the idea is, once again, you scaled down your base. You had a 16, it went down to a 4. You didn't have a 4 and then make it go up to a 16. So this process here is incorrect. This would be fine. And this would be fine. Then this just follows through over there. I hope this is helpful.